All right, welcome back. And now we're going to do section D, and we're going to talk about different logarithmic scales. We're going to talk about earthquakes, sounds, and acids. So let's talk about distribution of earthquakes. So we look at the map here. This is the map that shows all of the earthquakes that have been known. Also, it's not surprising. This is also the where you find the most volcanoes as well. This is called the Ring of Fire, actually, if I recall right. Okay, so now earthquake magnitude scale. The magnitude scale for earthquakes is defined so that each magnitude represents about 32 times as much energy as the prior magnitude. So the magnitude M is related to the released energy E by the following equivalent formula. So we have a logarithmic formula. Okay, let me show you this. So we have the logarithmic equation, right? And then we also have the exponential equation. It's the same formula, just one is solved for E, and the other one is solved for, well, they're both, well, one is in terms of solved for E, and the other one is a log, just has a log in it. So you just, all you have to do is take the log. What they do is they take the log of both sides, and they use the property of logs to go from the exponential to the logarithmic. Now, the energy is measured in joules, and then magnitude has no units. Okay, now using the formula for earthquake magnitudes, calculate precisely how much more energy is released for each one magnitude on the earthquake scale. Also find the energy change for a 0.5 change on the magnitude scale. Now here's the thing, we already know from the last slide that the way it's defined or set up is that each magnitude represents 32 times more energy as the last magnitude. So we should get a factor of 32 when we do this, or something close to 32. So let's see if it works. Okay. So the way we're going to do, whenever we're comparing things, we're going to divide. Okay. So we're going to look at the formula for each that gives us the energy, right? So this is the exponential formula, right? So this is giving us the energy released for each magnitude. So M stands for magnitude. So we could do this going from 1 to 2, 2 to 3, 3 to 4, it doesn't matter. Okay, so what we're going to do is we're going to divide. Okay, so the first term, so the first term, 2.5 times 10 to the 4th, is a constant number. So that is the same no matter what value of the magnitude we make, right? So this part here is the same. That doesn't change. So it's just this part here with the 10, with the exponent, that will change, right? So if we divide one magnitude divided by another using this formula, the 2.5 times 10 to the 4th is going to cancel anyway, okay? So the magnitude is really dependent on only the second term, which is this part right here, like I showed you, okay? Now, each time we raise the magnitude by 1, again, like I said before, we can go from 1 to 2, 2 to 3, whatever, 5 to 6 is like what they say here. The increase is going to be by a factor of what? 10 to the 1.5, right? Because that's what we have here, right? So we could look at it as 10 to the 1.5 raised to the m power, right? Using the power rule for the property for exponents, right? So every time we increase by one magnitude, it's going to increase by a factor of 10 to the 1.5 power, okay? Now, the cool thing is if we take 1 to the 1.5 power, we get approximately 31.623, which is, if we round, gives us that 32 that we were given at the very beginning when we started talking about this scale. Okay, so again, makes sense from our previous discussion, and it's true based on the formula. Okay, now what if we do half? Right? What if instead of 1 magnitude, what if we do half of a magnitude? Then all you have to do is you're just going to use m as 0.5. And so we get approximately 5.6 times the energy. So, and here's the thing. So just because you're half a magnitude doesn't mean it's half of 32. So it's not linear. It's not linear. Remember, it's not linear. So just because you go up half a magnitude doesn't mean it's going to go up, the amount of energy released is going to go up by half of that. It's not. In this case, it's only approximately 5.6 times the amount of energy. All right, now in 1989, San Francisco earthquake in which 90 people were killed had a magnitude of 7.1. So calculate the energy released in joules. Compare the energy of this earthquake to that of the 2010 earthquake in Haiti, which had a magnitude of 7.0 and killed an estimated 316,000 people. Okay, so now what we're going to do is let's figure out the amount of energy released when we have a magnitude of 7.1. So in that case, all we're going to do is use the energy formula and just plug in 7.1. Okay, so when you just put in 7.1 and just plug it in your calculator, we get approximately 1.1 times 10 to the 15 joules of energy. Okay. Okay, now, if we compare that with the Haiti earthquake, which was a magnitude less, or excuse me, 1/10 of a magnitude less. So it wasn't as strong as the 7.1. Okay, so if we look at the 0.1 difference, we're looking at that the magnitude, the amount of energy is 1.4 times as much energy. Okay? So if you increase by a magnitude of 0.1, then that's going to be 1.4 times as much energy as 0.1 before that. Now, which is not that much, but nevertheless, but here's the thing. It was stronger for the one in San Francisco, but it didn't cause as much damage. The Haiti earthquake, which was less in magnitude, but killed a lot more people, has to do with the lower quality building construction and lack of resources in the immediate aftermath of the quake. Okay. All right, now let's talk about sound. So the decibel scale is used to compare the loudness of sounds. Okay, so in the earthquake scale, we were comparing the amount of energy for earthquakes, right? So in the decibel scale, we're going to use to compare the loudness of different sounds. Excuse me. Okay, so now the loudness of a sound in decibels is defined by the following equivalent formulas. So again, we have a log formula and we have an exponential formula. So the loudness in decibels is given by this log formula. Okay, notice that the log is a ratio. It's the log of a ratio where you're comparing the intensity of two sounds. There's the intensity of the sound that you want to compare, and then there's the intensity of the softest audible sound to the human ear. Okay, so the intensity of the softest audible sound to the human ear, that's our baseline. Okay, so that's always going to be the same. Now, the equivalent exponential form of the equation is at the bottom there that I just boxed. Okay, so again, all they did was rewrite the formula by taking the exponential of both sides with a base 10. Okay, so they're the equivalent formula, just solved differently. Okay, one is solved for loudness, the other one is solved for intensity. So now here's a typical decibel scale sound. So notice that the softest audible sound has a decibel of 0, that's the baseline, and that's 10 to the 0 power, so that's 1. So notice that each decibel is equivalent to how loud it is compared to the softest audible sound. So if you're 10 on the decibel, then you're 10 times, right, as loud. If you're 10 to the second, then you're what? 10 to the second time. So 100 times as loud as the softest audible sound, and so on and so forth. Okay, so notice that the decibels is basically just 10 times the exponent. Okay, but again, this is a common table here, so we're going to refer to this table in a couple of examples. Now, suppose a sound is 100 times as intense as the softest audible sound. What is its loudness in decibels? Okay, so again, we're just going to use the formula. So we're looking for the loudness in decibels, so we need to use the first form, which has the decibel scale for it. So it's going to be the log formula. So because we want to know what the loudness is in decibels. So we're going to use this formula, and of course, we're going to use the intensity of the softest audible sound, which we know, and then we're going to compare that to the intensity of the sound that we want to look at. Now, what we do know, though, is the ratio of these two sounds is 100, because we're saying that it's 100 times as intense as the softest audible sound. So what that means is this ratio, what they're telling us is this ratio is equal to 100. Okay. And so in this case here, that's why we put 100 in here. And of course, if we use logs, if we have log base 10, and we change this 100 to 10 to the second power, the log base 10 and this exponential cancel each other out using the property of logs, and we end up with 10 times 2, because this log base 10 of 100 reduces to 2. And so the decibel is going to be 20, which makes sense because if we go back to the scale, 100 is right here. So 10 to the second power, which gives us a decibel of 20, which is basically equivalent to a whisper. All right, now, how does the intensity of a 57 decibel sound compare to that of a 23 decibel sound? Now, here's where, when we're going to compare these two, we're going to divide them, right? So we're going to divide the two formulas. And we want to compare the intensity. So we're going to have to use the formula that involves intensity, the exponential. Okay, so again, we're going to take the sound, the intensity of sound 1 and compare it to the intensity of sound 2. And so we're going to divide. Okay, so how do we get to this formula? Just so you know, what are we doing? We're taking the intensity of the sound. So again, if we go back to the formula, right? Or excuse me, the second one here, this one. Okay, we're going to use the two sounds and we're going to divide. Okay, so now, oops, yeah, here we go. Okay, so if we do intensity of sound 1, that's going to give us, we're going to divide. So it's going to be hold on, I want to make sure. Yeah. Okay. So when we're taking the intensity of sound 1 divided by intensity of softest audible sound, and then we're divide that by the intensity of sound 2 divided by the intensity of the softest audible sound. Notice that the intensity of the softest audible sound cancels, and we end up with exactly what we have here at the bottom. Now, what does this mean here? The top here equals what? 10 to the exponent of what? Loudness in decibels of sound 1 divided by 10. And then the bottom one is going to be similar, 10 to the loudness in decibels of sound 2 divided by 10. Now, the property of exponents says that, hey, if you're dividing two exponentials with the same base, you subtract the exponents. So that's how we get this, because we just take the top minus the bottom, which is what we get here. Okay, so just so you see how it's derived. So it's just not pulled out of thin air. Okay, now what we're going to do is basically just substitute in the loudness for each sound into the formula. Right here. And so when we simplify in our calculator, we get 2512. And so the comparison of the two sounds, the intensity of sound 1, that's at 57 decibels, is more than 2,500 times more intense than sound number 2 at 23 decibels. All right, now let's look at something called the inverse square law for sound. The intensity of sound decreases with the square of the distance from the source of the sound, meaning that the intensity is proportional to this. Okay? So it decreases with the square of the distance. And this is called the inverse squared law with distance. So it says, how many times greater is the intensity of a sound from a concert speaker at a distance of 10 meters than the distance at a distance of 80 meters? Okay, so again, whenever we're comparing, we're going to use division. Okay, so we want to compare the intensity, and we want to know how many times greater is the intensity. So we're going to look at using the squared distance, right? We're going to use the inverse square law for distance. Okay, now the sound intensity at 10 meters is 64 times as intense as 80 meters. Well, how do we reach that? Well, we take the 2 meters, right? And what do we do? We take 1 over 80 squared divided by 1 over 10 squared. And what do we do? What do we get? Well, the top one, oh, actually, if we have, this should be 10. And this would be 80. So now if we simplify this, we actually get 80 squared over 10 squared, which reduces to, well, gives us, 6,400 divided by 100, which gives us our 64. Okay, so that's where the 64 comes from. Okay, and all we're doing is we're using the fact that the inverse square law for distance says that the intensity is proportional to the 1 over the distance squared. So if we know the distances from a source, we could figure out how much more intense it is based on the distance using this formula. And again, just by dividing. All right, so now how far should you be from a jet to avoid a strong risk of damage to your ear? Okay, well, let's look at the chart. Okay, so here, strong risk to damage to the ear is 120 decibels. Okay, and we're looking at a jet at 30 meters is 140 decibels. Okay, so that's what we're going to use. Okay, now table that we're just looking at shows that the sound from a jet at a distance of 30 meters is 140 decibels. And 120 decibels is the level of sound that poses a strong risk of ear damage. The ratio of the intensity of these two sounds is given by, again, we're dividing by the two intensities, right? And so we're using the two formulas. And so when we do the property of exponents, we get what? We get 10 to the 140 over 10 minus 120 over 10, which equals 10 to the 14 minus 12, which gives us the 10 to the 2, which equals 100. Okay, so now that is the ratio of the intensity. So we know that the intensity of the jet at 30 meters is 100 times as intense as the minimum number of decibels before, or what should I say, the threshold for ear damage. Okay? So now if we use this intensity, right? So again, the sound of the jet at 30 meters is 100 times as intense as the sound that presents strong risk to air damage. So if we want to prevent air damage, we need to be far enough away from the source, okay? So that means that you have to be far enough from the jet to weaken its sound intensity to at least a factor of 100, okay? So because sound intensity follows the inverse square law, then what do? Well, we have to, by moving 10 times as far, right? So that means, remember, 1 over the distance squared, right, equals, right, we want the distance squared. We want, when we, how do I want to say this? It's going to be 100 times, right? Because we want to reduce the intensity by at least a factor of 100 through the distance, right? And so what we're going to do is we're going to use this formula here to figure that out. Okay? And so we want to reduce it by a factor of 100. By doing that, well, we're going to use the fact that that means to get 100, we use the fact that it's equal to 10 squared. And so in this case here, 1 over 10 squared, which means the distance is going to be 10 times as far. Okay, so if we're at 30 meters from the jet, and that's at 140, that would mean we need to go to 300 meters in order to get the sound down to a safe level, or just at the threshold, which is 120 decibels. So that's why it says more than. We want to be more than 300 meters away. And that would be a safe distance. All right, now let's talk about the pH scale. Now the pH scale is used to classify substances as either neutral, acidic, or basic. Okay, so the way the pH scale works, it is based on a log scale. Okay, just like the decibel scale and the earthquake scale. So the way you read this is pH, which is again just a number. It's a unitless number. pH is is equal to negative log base 10, so it's common log. And this here means, it's a symbolism, so it means the concentration of hydrogen atoms in the that are present. Okay, so it could be a liquid, it could be typically it's a liquid. Okay. Now, also, we've got the equivalent exponential equation here. So if you wanted to solve for hydrogen concentration, hydrogen ion concentration, you could use this formula here. But if you're looking for pH, you would use this formula here. Okay, now, pure water is neutral, has a pH of 7. Acids have lower pHs, and bases have higher pHs. So anything lower than 7 is considered acidic or an acid. Anything higher than 7 is considered basic or a base. And of course, there's weak and moderate and strong bases and acids. Okay, so here are the typical values for different types of bases and acids you might find around the house. Okay, now here it says, what is the pH of a solution with a hydrogen ion concentration of 10 to the negative 12 moles mole per liter? Okay, is it an acid or a base? Well, right away, if you look at the formula, notice that the hydrogen concentration is 10 to the negative pH. So if you want to look at concentration, you could just look at the exponent, and the exponent will give you the pH. You just have to take, it's the negative of the pH, okay? So if you look at here, this has a negative 12, so I'd say the pH is 12, and so this is going to be a base. But again, you can use the formula, because all you have to do is take the pH negative log, you take the negative log base 10 of this, right? So notice here when you plug it in that this is a log with the base 10, and this is exponential with the base 10, and so the property of logs, when you see exponentials and bases composed with each other, if they have the same base, they cancel each other out, and so you get a negative of a negative 12 because the log and the exponential cancel each other out, and you're just left with the 12. So then you get the 12, which is what I said it was going to be anyway. So this is a strong base. All right, that's it. And again, if you have any questions, please reach out to me. And again, you have many different resources. I have my office hours. If you're taking this class and I don't have office hours during the semester, then please email me, or definitely use the Tutoring Center. That it is a great resource. Also use this tools available to you on my math lab as well. Okay, have a great day.